Assalamu alaikum, everyone. So we are on lecture 13, EE341, microelectronics. Right. So we will continue from the last point where we left. We are going to still discuss the frequency response. So if you have any query, make sure to please come in the office hours or in the class window. Class window, you can come in the Zoom, and office hours you can come in person. We just share the details, like either you have to contact me or Dr. Wala. So you can just contact. So frequency response, basically we were talking about, and in the frequency response, we have seen till now multiple things, and so that I just give a brief overview and then we will build on top of it what we are going to cover today. So we have seen previously the Bode plot, okay, how we can use the Bode plot to, if we have pole and zeros information, how we can do the magnitude plot, okay. And then after the Bode plot, we have seen, okay, now we have the Bode plot, how we can use simple the pole information at a certain nodes to have a frequency response or to get the information about the poles. And once we have the poles, we can draw again the Bode plot. So we saw the analytical approach, I would say, analytical approach. So analytical approach, okay, or intuitive approach. Okay, now or intuition, we have seen how we can determine the poles from a circuit. Okay, so we have seen, okay, if this is a simple circuit, a common source amplifier where input is here, where output was here at this point. Okay, this is a VDD, this is an RD. So, and there's a load capacitance. So how we can determine ultimately the pole. So we saw, okay, at every node, you can just need to see the capacitance from that node to the ground, and also the impedance from that node to the ground. And that ground is going to be considered in a small signal model. So it's going to be AC ground. So VDD will be also for us AC ground. Okay. So that we have seen, and then we can determine the poles. And then we said, okay, we talk about those capacitance which are between one node and the ground. But what about this configuration? When we have something in the middle, when there's not like there's a floating node that's not connected to ground. So then we saw a powerful concept of the Miller capacitance. Okay. So we saw the Miller effect or Miller theorem, how we can separate this one, the green one, which is CF, into two independent capacitance, which are from this node to C in and from here to C out. So we also have seen this thing in the last lecture. We are going to use all of these things in today's content. So we have a lot background, but now we need to move forward to have one or two, and then we can go for the analysis approach. So for today, if we just, I will draw some circuit, and it's a basic elementary circuit one analysis, but that's going to be helpful to make the story for us. So we have a capacitance here, and we have a resistance here. And I want to determine my output at these two nodes. V out is here. Let's give it a name R1. So my input is here, output is, I'm taking the output on the resistor. Just 1 minute, even if you want to think, pause the video and think that, okay, what this circuit is, what V out over V in will be. If I talk about this characteristics, which you have seen before, that was somehow coming as a low pass configuration. Why? So we have something like this. So roll off was coming here, we say cutoff frequency here, it's passing everything. And here it is stopping. So low pass, it's allowing the frequency in this range and stopping here. So it was a low pass filter, right? So because of the CL, what CL was doing, CL was creating the impact of a roll off, or was reducing the amplitude at a higher frequency. But what about this circuit, which is down here? Is it also low pass? We need to see, but I don't think so. because I'm not taking the output at a capacitor, rather I'm taking an output at a resistor. This one, which is a low pass, that was equivalent to something like this. V in, sorry. So V in, if I have a resistor here, and then I have a capacitor here. Okay, and I'm taking V out. So whenever I take output on the voltage, what happens, the output on the capacitors, what happens, the voltage start reducing based on the capacitance value at a higher frequency, because this starts playing its role. It's ultimately a voltage division. But what about vice versa? If I do the vice versa, the relation, let me draw the curve and then we can discuss about the relation. So the relation is going to be something like this. So it's a high pass frequency where the cutoff is going to be decided by, again, inverse of 1 over R1 and C1. So they are going to act as a pole, the same notion. This is a node. So we are going to see the impedance R1 and C1. So 1 over R1 times 1 over C1, which is going to decide the pole or the cutoff frequency, or the role of frequency of this high pass filter. So we can also create a high pass using a MOS. So we are going to see that, but let's just put this math here. So V out by V in, all of us know, is going to be, we are taking an output at R1, so voltage division R1 plus, if I want to write in the form of impedance in S domain, is going to be 1 over SC1. Okay, and we just do this basic math. R1 SC1 will come up. Let's put it here. This is a product 1 plus SR1 C1. So this is going, if we just want to plot this thing, the behavior is going to be like this. And if you just want to separate the magnitude initially, we can just take the mod value. V out by V in mod will be equivalent to just taking the square and getting rid of that S thing. So we can write it R1 C1, which is omega, meaning S is equal to J omega. So we're just replacing, if you just want not familiar or if you want to refresh, we just replace S is equal to J omega in this and take the only the real part, meaning magnitude part, by taking the square. So now this is going to be omega is equivalent to 2 pi f. So it's a frequency dependent for us. Okay. So that's why the variation is coming. So it's not going to be consistent. So if we want to draw this thing, it's going to be 1 plus R1 square, C1 square, and omega square. Okay. So ये अब आपके पास relation आ जाता है, and what we can observe at a higher frequency, this is almost equivalent to 1, because this 1 will be very much less as compared to this R1 square, C1 square, omega square. So this will be equivalent to R1 square, C1 square, omega square. It will cancel out. So R1, C1, omega will be cancelled out by the down, and the V out will be equivalent to 1 at high frequency. So at high frequency, everything is being passed, whereas at the lower frequency, the signal or the gain starts getting reduced. So that's the basic concept about which we are interested. But now let's apply the same concept to MOS. MOS, do we observe the same thing? Do we observe the high pass characteristics? And that's something very much interesting for us to know. So for the MOS, there's an example. Let me write the example since we are at chapter 11. So 11.11 example. Let me just do that for you, because that is bringing a lot of notions. So it's again a simple amplifier where we have a biasing network to bias your gate so that you can, and there they are bringing a notion of an input capacitance, CI. Okay, I will just couple of a moment talk about this CI and what type of amplifier this is. I want all of you to just ponder what type of amplifier this one is. So here. Can anyone think about it? So we have an input which is applied to the gate of an amplifier, and we have an output which is we're getting from the source of an amplifier. So this is a source follower, or not common name also can be common drain, because the drain is AC ground. So it can be again AC ground. Both the things are we can use. And here we are just using on a source, a current source. So current source, the source is going to see a high impedance that is required so that we output gain or our gain is somehow equal to unity. So we have here a coupling capacitance, which we normally call a coupling capacitance, a biasing capacitance, okay, biasing capacitance, and the source follower or a common drain, commonly also known as a buffer amplifier. And we all know where we use buffer amplifier. Whenever we have certain load to drive, we have a higher value of CL, and we want to derive this thing so that our normal gain doesn't get impacted. What we want a buffer, which is going to create a buffer zone between the output and our preceding in output state. So now when we create something and a buffer amplifier between this and output, which is a high CL, and this our old amplifier, this is a buffer we're placing. So we get the characteristic so that our circuit doesn't get loaded, our output gain doesn't get reduced, and we can get the same configuration by the addition of a small buffer. Definitely some area constraints are going to come and you have to design a separate amplifier. But that's not the main goal of this intuition. But the main thing is that they are saying, okay, we need to design a buffer amplifier or a source follower to achieve a high quality audio. Okay. They are not saying, okay, you need to design this common source or common gate amplifier. They're only concerned about designing a buffer amplifier, right? When they are talking about designing this buffer amplifier, so we have this buffer amplifier and we need to decide the value of this C in and this CL. And also we can decide the value of this RD, which is being provided, and we are provided that, okay, you can assume lambda is equal to 0. Okay, and we just have the value of your GM. Let me just make it back a bit. GM, which is M1 here, so it's GM1 is equal to 1 over 200, and RD, which is the load resistance, is provided as 100 kilo ohm. Okay, so these are the values which we are going to use in the design, and they want us to find out C in and CL, the maximum values for both of these things. Before proceeding, we need to identify what the C in is doing and what the CL is doing. We know from our previous common source configuration, the CL was ultimately coming at a load and was doing that high frequency cutoff. So if I want to draw the plot of an audio frequency, if this is my frequency and this is somehow the gain of my audio, so this is, I want to have a high quality audio in a certain band, and then it should reject in certain band below and after. So there should be rejection here and there should be rejection here. And we know the audio band, since it's high quality, so I would like to cover all the frequencies which are in the audible range. And if I want to talk about the audible range for an audio, what is those frequencies? We know this is 20 hertz. And we want to find them extreme values. Definitely somebody say, okay, why 20 hertz? Why not 100 hertz? Yes, we can have it based on your requirement, but at this moment, the requirements are that we want to have a high audio amplifier, which is going to cover the complete range, and this should be 20K. So what we know, this is going to be decided by this side, which is what? Which is a CL times whatever the impedance seen at this point. So I can write, now we know the information, if this is a node pole, let's say omega P2, this is omega P2. Omega P2 will be equal to 1 over CL, load capacitance, time the impedance seen at this point. What is the impedance? We're seeing from the source side. So from the source side, the impedance is going to be 1 over GM1. So it's going to be CL times 1 over GM1. Or I can write omega P2 will be equal to GM1 times divided by CL. Yep. So you can just check also from the example 1.1 if you have any confusion. But the main essence is that we want to find the at this point. And what about this 20 hertz? Let's say it's omega P1. And what is omega P1? This is this capacitor, which is a coupling capacitor, which is a DC blocking capacitor ultimately. So blocking the value of DC because it's coming in a series of an input. So anything coming in a series of an input is going to block the DC value in reality, depending upon its value. So this omega P1 will be ultimately equivalent to, if we just want to write it, it will be the pole at this node. Again, this is one node. So this is going to be an AC ground in a small signal. Vin will be shorted when found to find an impedance. So from this node, if I want to write omega P1 will be equal to 1 over C in times RD. So this pole, which is ultimately the low frequency side pole, or which is deciding ultimately my high pass corner, is equivalent to what? Is equivalent to 1 over omega P1. We can put 20 hertz since we know that we want to set this thing C in, we want to determine, and this is given as 100K. So we can find the C in will be almost equivalent to 79.6 nanofarad. Similarly, from this expression, we can find C out. GM1 is given to us. C out will come out to be 39.8 nanofarad. Okay. So we can find the capacitance using this way. And interesting thing, if you see this capacitance value is nanofarad, this capacitance value is nanofarad. If I want to put a circuit, make a circuit and integrate circuit on chip, and I want a capacitance value of nanofarad, it's not possible. So I cannot have that much huge value in an integrated circuit. I'm not talking about the discrete component. I'm talking about an integrated circuit, meaning on this small IC, if I want to embed a very much capacitor of this value, it's not possible because it's going to take huge amount of area. That will be more than this chip size. So that's why that's another topic which we are going to come in a later. But at this moment, the whole idea is that for this much high frequency, I need to have for this much low frequency, meaning 20 hertz cutoff, I need to have a very much high value of a capacitance. Okay? And also we can observe this configuration, which is I'm marking it as a green, is equivalent to the same circuit जो हम लोगों ने अभी last slide में देखा था. It's equivalent to something like this. C in, and I'm taking my output at a RD. So here I'm taking my output and this is my C in. So this is the node, अगर आप इसको Vx कहना चाहें, so this is the same thing जो हम लोगों ने अभी last में देखा था. This is your V in. So if I'm taking as a resistor, I am having a high pass characteristics as compared to low pass. And in generic, we call this thing as a mid-band gain. Mid-band gain. Okay? So we have a low frequency, we call it omega L, and high frequency omega H. Let me draw. And this is omega, not F. So it's just the same thing, 2 pi F, constant multiplication, but just to make sure. So if I want to write a proper circuit for this thing, I'm gonna write it. Let me draw it. So this is your omega. So commonly known as, this one is known as mid-band gain when we are going to talk about mid-band gain, or the commonly known as DC gain, which we talk about. Because now we are bringing the notion of an input capacitance, which is basically a coupling capacitor or DC blocking capacitor. That's why our old DC calculations are going to be called as a mid-band gain, where the role of starting is a high frequency, the dominant frequency, which is deciding the bandwidth, and this one is the low frequency. Okay, and here is your magnitude, whichever the way you want to write. Okay, so this is your magnitude. So that's why we normally define. Now the interesting thing is that why I'm using that C in. What is the benefit of using the C in? Why I'm interested in this configuration? Why not I remove the C in? I remove C in and not do this behavior. So there are multiple answers to this question, why I need C in. So first and the basic thing is that Cin is a DC blocking capacitance. Sometimes I don't want, in a low frequency applications, I don't want to have any amplification of the DC side. DC is coming because of the motion artifact. DC is coming because of some errors. So we want to get rid of DC value, get rid of DC. So also, if I want to get rid of DC, I should have a high pass filter characteristics at a 0.1 hertz, 0.10 hertz, whatever the related frequency. Something similar to the audio application. I don't want the frequency below 20 hertz to be amplified. Or I don't want, for example, frequency below 100 hertz to be amplified. Then definitely I need to have a coupling capacitance. Can be another way, but that's one of the way to have a DC rejection. So I need one thing. And second thing, we talked about the buffer, the source, the buffer, the common source amplifier is normally used not for the amplifications. The gain is almost or less than 1. So we use it as a buffer, meaning it's going to be connected with a common source amplifier or common gate amplifier because we are using it as a buffer. So for that, if I just draw a simple buffer and I will bring this analogy why this one is important. Let me just, yeah. So if I want to draw a back-to-back, a buffer and it means your common source amplifier followed by a buffer. So if we want to draw, let's give it to the name M2 and keep the other name V in RD same, and इसको RD1 कह देते हैं, and keep the same thing as which we just drawed. So ये आपके पास पुरानी stage है which I drawed in the previous slide. This is C in, this is RD, so this is RD1. So here we are having a gate like this. So this is a source follower here came. So we gave the name M1. So let's keep the name M1 here and let's keep this thing. There is a load capacitor which I'm not drawing because that notion there's nothing more we want to clarify at this point, and this is VDD. So this can be a one configuration, which we just did the coupling capacitor one, and second configuration can be something like this. Don't put a coupling capacitance like this one, since we just need this M1 as a buffer, and that's the reality. We need M1 as a buffer, but let's not add the coupling capacitance. What's going to be the difference? So now we are directly feeding this without this coupling capacitor to this point. This is grounded. This is again. Let's just, this is your V out. And we just directly connect this point here. Here you can see now we don't need separate RD here. Why? Because this RD is setting the bias point. If you see what we are doing here, this RD is doing, it's also setting the bias point. This RD here is setting the bias point for the source follower, because the source follower has to be an amplifier, meaning it needs to be in saturation. So somehow we need to set it a voltage at this point. So we can only set using some intermediate, because here we cannot feed input from outside. So we are feeding from this VDD. So a voltage division is happening and we are setting some value here. Okay. If I use this C in, I can independently set the values for M1 and M2 by using a coupling capacitor. A coupling capacitor helps me in independent setting the bias potential of M1 and M2. Why? Because capacitor blocks the DC value. So no DC is going to be forwarded here, and I can easily set the value and I can have freedom over M1. Whereas in the circuit 2, I don't have that freedom. Now this value is being set by RD1, and the same RD1 is controlling M2. So my gain will be reduced for the M2 if I want to get benefit for the M1, and vice versa. If I want to find a set value much good for an M1 for the biasing, my gain value will be reduced. So it's not going to be straightforward. That's why we bring the C in as a coupling capacitor, which is going to block the DC value. It's going to give us benefit in terms of implementation. So this is a common configuration which we normally use whenever we use a source follower. So the capacitance is needed for multiple reasons. First, we want to have a isolation, and for isolation not only in terms of operation but isolation in terms of selecting the value so that we can operate at an optimal position. Now whatever the value, we can set it for ID in this configuration and we can use it. And second thing, we also want to remove the DC values. For both of these configurations, we need to have an independent selection. Okay. So if you have any concern or comment, just make sure let's go through this one and update us so we can try to clarify your confusion. Now, after this, we come to the main point that why we did all of these things. So till now, we didn't bring one notion. We just have brought, okay, the capacitance which we are bringing as a designer, CL, which the amplifier is going to see at the load capacitance, and C in, just हम लोगों ने अभी देखा है, that is some capacitance which we are bringing in the circuit for the biasing, for the coupling, and also for removing the DC. But there are some other capacitances which are inherent to your MOS or inherent to your BJT. We are talking about the MOS, so inherent to your MOS transistor. What are those capacitances? Those capacitances are commonly known as parasitic capacitance. So those parasitic capacitances basically ultimately affect your frequency response. When I'm talking frequency response, I'm meaning high frequency response. So the low frequency response, this C in basically impacts. But for high frequency response, those parasitic capacitance are going to impact. And what are those parasitic capacitance? I will just draw brief a little bit about, and then we can see. So there are three types of capacitances, which are basically main impact. You see, this is the gray gate, this is the drain, and this is the source. So first thing is that between the gate and the channel. So channel is formed by what? Between the drain and source. So one capacitance is between gate and drain, and one capacitance between gate and source. And the CGD and CGS. So these are the capacitance which are commonly called as channel capacitance. So they are channel capacitance, okay, and they are going to impact your system. And apart from that, we have a drain, and drain, we have a bulk, a body, fourth terminal. So there's going to be CDB, and source to bulk, so not shorted together. So we have these three types of capacitances: channel capacitance, drain to bulk capacitance, and drain to source capacitance, which have a dominating effect, which we conductors, and in between there's an insulator. Capacitor is going to be formed. So if we see the MOS configuration, we have these three sort of capacitance. Let me draw the MOS view if you want to analyze it, just for your information. You most likely have seen the devices course. So here's the channel basically. And channel forms here, and here we have some silicon dioxide. This is your channel, all, and here your gates. So we all know silicon dioxide is an insulator. This is your, for example, a source. This is your drain. In NMOS is going to be highly n-doped, and we have a P substrate which is going to be here. And P substrate is something which we normally have a bulk. So we will see that it's not like, let me draw exactly the same. So this is your, doesn't matter because they are interchangeable. Let's do. So this is your drain, this is N plus highly doped, this is S N plus. Okay. So between the gate, this is a conductor gate, and there's an insulin. After that, there's again a conductor. So it's not going to be capacitance, commonly known as CGS. Same thing here. CGD. And similarly, from drain to body, so it's a body here, so we can have a capacitance CdB. If drain and source and bulk are not shorted, we have a capacitance between source and bulk. Okay, so that's what we normally have, all of these impedance, the capacitances, and we call these capacitances as parasitic capacitance. We are not bringing these capacitance as a designer; they are coming because of the inherited property of. Right. Yes, there was some small glitch. Let me just pause for a moment before we are back. Yeah. So we are there. We are here that okay, these capacitance are known, commonly known as parasitic capacitance, and they depend upon width and length for us. So if we want to mimic from where they are coming, let's draw. Let me draw in a next page so we can see all of them, or I can draw here and then we can go to the next page to have a more complex circuit we can observe. So let me just draw a simple same common source, or just a MOS, for example, or a common source. So this is a gate, this is drain, and this is source. Let's a little bit pay specific attention. Okay, and I'm not plugging this source at this moment to ground. I'm just keeping at this moment as it is because I want to just identify the parasitic capacitances, and also we'll see the small signal hybrid pi model, how it changes. So this is a gate. So we say one capacitance between gate and drain. Let me use a different color here for the capacitance. Make sure recording. Yeah. So between a gate and drain, there is one capacitance, commonly known as CGD. Between gate and source, there is one capacitance, commonly known as CGS. Between the drain and the body, because the body in the is grounded, so that's why we can say in case of NMOS, CDB. In case of PMOS, it's VDD, but still an AC ground. And since I didn't say the source is grounded, so I can say source and bulk also we are going to have. So these capacitances, which we all going to have, all of these capacitances, we need to bring in our hybrid pi model. So let me draw the hybrid pi model in the red, and we'll add these capacitances in the green then, okay, to identify the thing. So we just have something we normally called VGS. Okay, and then we say, okay, we have our GM, VGS, and we say, okay, we have something like RO, for example. So now let's draw and this is the drain point, for example. This is the source point for us. Okay, and this is the gain. So I just draw these terminals. Let's draw the capacitance. So first, the capacitance is going to be now, if we see in terms of capacitance, the gate and drain have a connection. CGD. What else? Gate and source also have a connection. CGS. And what else? We talk about drain to bulk. Drain to bulk. What else? Drain to source. So drain source to bulk. So we have all these capacitance. Again, as I mentioned, there can be other capacitance, but these are the dominating capacitance which can impact our circuit. So we need to analyze these capacitance explicitly. Okay? And also, if for example, my source, if I have this configuration and my source is connected to body, or both of them are grounded, my CSB will be equal to 0 because they both are shorted together. Then I will not have any CSB capacitance. So based on the specific scenario, we will use our capacitance accordingly. Okay? So let's draw another one, and to understand if they are back-to-back capacitance, how the circuit is going to be impacted. And then we will move towards analysis. I will most likely point out the analysis point, and then we can move in the next lecture towards more detailed discussion. But I want all of you to absorb these things because they are, again, might be basic concepts, but they are fundamental and they're going to use a lot in our analysis. Okay. So here we have one NMOS and a PMOS is connected as a diode connected on top of it as a load. So M1, we are taking V out here, and we are having an M2 here. And what our task is to identify the capacitance of this network and how we can analyze them. Because at this moment, we all know what is going to be the gain of this thing, but in terms of analysis, in terms of capacitance, we don't know these things. And also one notion which I want to bring in the last one, if we see that, yeah, doing this only this configuration was relatively easy for us in terms of a hybrid pi model. But when I bring all these capacitance, the analysis will become difficult. We can do analysis using this hybrid pi model by bringing all the capacitance, but our hand calculation will be very much clumsy. So the best way is have the small MOS model without capacitance, find the midband gain, and bring those concepts of Bode plot, the finding the pole at a specific node, and the Miller capacitance, and then find the overall transfer function. That's why we utilize, or we brought those notions earlier. Now we can apply them in a plenty of applications or examples, and we can see this analysis. Yeah. So let's do this thing. Let's first draw, just again for simplification. You don't have to all the time draw all the capacitance. If you can short some capacitance, you are free to do that thing. But what I'm doing, I'm just drawing all the capacitance first, and then we can move forward. So for simplification, I will just do this thing again, redraw this thing. We'll give some space so I can redraw all the capacitance. So one MOS ultimately have 4 parasitic capacitance, which we normally assume. So here, this is M1 for us. This is M2 for us. So what we all know that this is going to be a short. So I will write something so make our life a bit easy. So we know that the V or source of source 1 and the drain bulk 1 are shorted. So the CSB, C source to bulk 1 will be equal to 0. So I don't have to draw this capacitor. Also, the gate and the drain CGD2, they are also shorted together. If something is shorted together, they cannot be capacitance because we need an insulator. They are short, so there cannot be any capacitance. So these two capacitance, I can easily get rid of it. And also, it's a PMOS. So for the PMOS, what we can do that the source is connected to VDD, meaning ground, and the bulk is also connected here. So we can see this thing. So C SB2 will also be equal to 0. Okay? So I can get rid of this capacitance too. So now I'm drawing the capacitance in the green. So first capacitance will be, we all know, will be CGS1. 1 stands for M1 and M2 stands for M2. Okay, CGS1. Then there is going to be 1 capacitance between the gate and the drain. So we get rid of 3. So we will be left with 5 overall capacitance if we just want to bring this notion. CGD, CD. So let's fix the notion proper. CGD1. Okay. So, and then there is going to be drain to bulk here. So CDP1. So for M1, all the capacitance are done because the CSB is 1. And for M2, we have 1 capacitance from here, which is going to be equal to CDB2. So that's 1 capacitance which we have basically. And then we have, because the gate and they are same, so we don't have to repeat that capacitance. This one is also gone. So we have 1 capacitance from this point, which we normally called it like here. We can, because they both are shorted, so we can write CGS2. Okay, so we can have these 2 capacitance. So there are 5 capacitance which we said we will have. But we also know these 3 capacitances are on the same node and they are parallel to each other. So we can simplify our circuit like this one. We in here again, I will draw the capacitance in the green for easy. So let me draw this capacitance here. This is C in, which is CGS1. We have one capacitance between gate and drain one, and here we have capacitance in parallel, meaning they will be added together. CGS plus CDB2, CDB1. So that makes our life easy in terms of analysis. Now we know that, okay, we have seen this complex, and now we come to this conclusion. We know all of these things are going to be added together. They will be multiplied by the R out here. We know that CGS1 is going to be multiplied by the input impedance. And we know the CGD1 is intermediate between two things. And that brings us back to the old notion, which we covered in the last lecture. And we just briefly took the name again into the start, Miller capacitance. So we will do all of these things in examples, but that's the whole thing why we learned those stuff. So we know each and every node. For each and every node, we can find the capacitance, we can find the impedance, we can find the pole information, we can plug that pole information in the Bode plot, and we can have our frequency response. If any capacitance is in between two nodes, we can use Miller capacitance to separate into two capacitance having fixed node between a node and a ground, and then we can again find an impedance and plug it the Bode plot and find the response accordingly. So that's the overall analysis. But let me write those analysis approach, which we are going to use in the next lecture to solve some examples and to have an idea. So for the frequency response, we will using this analysis approach or procedure for all the things. So now we have almost all the tools to have a complete response. We know the gain, how to find the gain of any amplifier. Now we know the complete frequency response analysis procedure. So the step by step, we will do that, this one. So let me just write it. It's also in your book, but just I'm mentioning here. So first thing, we need to determine which caps. For capacitance, I'm going to write caps. So for easily, which capacitance impact the low frequency region. Okay, basically the DC blocking capacitance. Okay, and we will see another example of source degeneration blocking capacitance, but at this moment, and we will see what capacitance are ultimately affecting the low frequencies. If I want to draw, we are talking about these capacitance, which are the high pass characteristics. Okay, and compute because we want to find, then we want to compute the low frequency cutoff. Okay, your high pass cutoff, your low frequency cutoff. That's very much important. For this analysis, we can neglect basically the main thing. We can neglect the parasitic capacitance. Parasitic capacitance, or your book is also using transistor capacitance. Okay, inherent capacitance. Transistor capacitance we can ignore because they are only going to impact the high frequency response. So that's first thing. Second thing, calculate the mid band gain. Mid band gain क्या है जो हम लोग शुरू से करते हैं, DC gain basically, mid band gain. तो हम लोगों ने उस mid band gain को करना है. Mid band gain करते हुए क्या करेंगे, सारे कैपेसिटर्स को इग्नोर कर देंगे. जो ये ऊपर वाले कैपेसिटर्स हैं जो हम लोगों ने फर्स्ट पॉइंट में देखे हैं उनको शॉर्ट कर देंगे, विल शॉर्ट देम. ठीक है, so we will not see any impact of those capacitors, and we will not consider any high frequency capacitance because we are only interested in this mid band gain. Okay? Once we are done with that thing, what we are going to do, we are going to identify and calculate basically the poles from transistor caps. ठीक है, तो ट्रांजिस्टर के कैप्स होंगे या कोई load capacitance है, उसकी वजह से we'll find the poles which are in the signal path. Again, for this configuration, we are going to ignore the first. We will again ignore or short the first part. जो हमारे ऊपर identify किए थे these capacitance for the low frequency, we will ignore them because they are not going to impact the high frequency. And now we are finding the high frequency basically. When we have all the pole information, we will use the Bode plot to plot using the Bode plot. But we will use first, we'll get this information and those capacitance which are, for example, in this configuration, which are in the middle of two nodes. So we'll use the Miller capacitance to convert into node and a ground. So we'll make sure that all those capacitance before we move toward the Bode plot are between a specific node and a ground. So we'll use Miller theorem to find equivalent capacitances for all of those things, for all of those nodes. And once we are done, then we can use the Bode plot to draw the frequency response and have the magnitude plot. And in the future, next lectures, when we will talk about a bit about the feedback, we are also going to about the phase. So this is the whole analysis which we need to do, and then we can do the plot, or you can also use some exact calculations to plot. But Bode plot is more than enough to have an idea based on the things. So these are the 5 steps or 6 steps which we are going to follow during our analysis. So just today's lecture, make sure you get accustomed to these things. In the next lecture, we will directly jump into some calculations, applying all the things on a common source, common gate, common source with degeneration, and we'll observe all of these things and what are the impact of the capacitances on our analysis. And that will conclude basically the overall how we can see a MOS transistor, because the MOS transistor, just all of you know, it has 2 main things. Gain, for a layman, we talk about the gain, and then the bandwidth, which we normally call a bandwidth. So by these 2 analysis, now all of us know that, okay, what is the gain and what is the bandwidth of our system? And then other things are definitely important and we need to know, but all of these things are linked with these designs. So that will complete the design of at least a single stage MOS amplifier, and we will then apply all of these things to a second stage or a multi-stage amplifier. Again, if you have any concern, question, please approach to us. You can come in office hours in person, and today's will be available just from 11 to 12. And also you can come in the class time, either on the Zoom, or if we are available in person, we will tell you, you can also tap in. Right, so assignment 3 is already, I guess, there, so make sure to submit on time. And we will also communicate the final exam, sorry, the midterm exam date ASAP. We just got the clash matrix from the RO office, so we will announce it, since as you know, the midterm exam is going to be in person. So we'll just announce the date at earliest. Right, so thank you for your participation. I'll just close the meeting now.